So we're going to start off talking about double integrals in polar coordinates. So this is a blast from the past, right back to the first unit, where we talked about, you guessed it, polar coordinates. It's not too much of a leap in terms of understanding where this stuff is going, because what happens is all we're doing is taking our knowledge of the polar coordinate system from two-dimensional coordinates and just swinging it on up into the third dimension, right? So basically, it's your unit circle or your polar coordinate system with height, right? So that's not too bad, really, when you think about it. I mean, if you look at the relationships that you see here, you have x equals r cosine theta, y is equal to r sine theta. That's all from unit 1. And z equals z. So no fancy relationship between z and something involving theta or a radius. It's just z is z. Z is the height. All right. So all the other relationships are still in play, like x squared plus y squared is equal to r squared. All right. That's the Pythagorean relationship. All right. Tangent theta is equal to y over x, but also z equals z. And so if I take you over to this diagram here, you see a lot of funny business going on. It's really kind of insane looking graph, but what we're looking at is really, like I said, the unit circle, and that unit circle is the base in the XY plane. But if I accentuate just a certain part of it, like this reference triangle, if I can get it to look halfway decent, it kind of locks in. It doesn't give me the perspective that I want until I modify it. Little modification. There we are. All right. So what we would be looking at, let me make that a little tinier. That would be the reference triangle. All right. So we would have an x value, a y value. Now the y value is indicated over here, because even though that's a parallelogram, or appears to be a parallelogram, it's still a rectangle. We have a y value, an x value, and r. That r didn't come out so hot. But that gives us the coordinate x, y on the xy plane. If you plot a point x, y, z, what you would be doing is going out x units on the x-axis, then going out y units parallel to the y-axis, and then shooting on up z units parallel to the z-axis. And that would give you some point that we would call x, y, z. All right. Well, actually, kind of overshot the mark. That's really just a vector. Let's say it's let's say I'm just kind of capping it off at this point right here. So I could call this point x, y, z. But if I tell you that x is equal to r cosine theta, and if I tell you that y is equal to r sine theta, then we have an ordered pair in the xy plane of r cosine theta, r sine theta. All right, now if you project that up into the z-axis, or parallel to the z-axis, you would get a new set of coordinates. See how that looks. That's all right. That we would call r cosine theta, r sine theta, z. All right. So that gives us a nice little relationship that allows us to navigate back and forth between polar and rectangular coordinates. All right. So if I need the polar analog, of a rectangular set of coordinates, I can work it out this way. Or I'm sorry, if I need the rectangular analog of a polar set of coordinates, I can work it out this way. All right. Yeah, no problem. I'll get it on appendix there. All right. But another way that we could actually measure a point in space would be based off of some value r, right, a radius outward from center. Now, if you're working your way outward from center, from the origin, that distance r could be in any direction. All right. So we narrow it down by establishing a theta. All right. So we established, so if that r could go in any one of these directions and everything in between, obviously. But if I say specifically, okay, we're going out r units, but following the angle of theta from the x-axis, which is 0 degrees or 0 radians. I'll just use the notation 0 to the rth power is another way of saying 0 radians. Then what I've done is I've gotten to the same location as xy. So what that does is that if I project it up into the z, parallel to the z-axis, it'll get me to the same location as xyz would. All right. So r theta z does the same thing. All right. Now, with that being said, we have a relationship between x, y, z and the r cosine theta, r sine theta, and z. But what about that r theta z? So if we focus, oh, that's a little thing. Nah, I can live with that. All right. So if we focus on that one, I can now say, well, r is equal to the square root of x squared plus y squared. I could say theta is equal to the inverse tangent of y over x. And you guessed it, z equals z. And you guessed it, I didn't leave myself enough room to write that. So shrink it down and put it in. All right, so out of all of this, we have lots of different relationships between the polar and rectangular coordinates. So what we're going to do is, that's super small now. What we're going to do is learn how to convert back and forth between the two coordinate systems numerically. And then we'll get into cases, we ended off the last unit by finding the volume under a surface, but I also left you that teaser problem. Now, I posted a solution to it, but I left you a teaser problem that we didn't really have as part of the, well, I'll call it the curriculum for the second unit. It was kind of to set us up for this unit. It's better served if you work that problem in either cylindrical or spherical coordinates, which we're going to get to in a little bit. All right, so we'll come back to that one when push comes to shove. All right, so example 1 here, convert the cylindrical coordinates to rectangular coordinates. All right, so if we know that these cylindrical coordinates are in the form of r theta z, then we can use that information to help us figure out what the x, y, and z values are. All right, so r is equal to the square root of x squared plus y squared. I cannot get a radical to look the way I want it to do half the time here. So that's a relationship that we can work off of. We know that theta is inverse tangent. All right, so we have those relationships that we can work off of. We know that x is equal to r cosine theta. We know y is equal to r sine of theta. But the one thing we could always rely on is z is e. And z is equal to z. So it's a question of, out of all 4 of these things, 1, 2, 3, 4, which is going to be the one that we would want to use. Well, you think about what you have and what you want to get. We have r and theta. We want x and y. So it would make sense to work off of these formulas. Actually, let me keep my highlighting consistent here. Work off of these formulas, because those formulas are the ones that involve r's and thetas but yield x's and y's. All right, so these are our basic formulas. Hang on to these, have access to them, but you still got to be able to select the correct ones. All right, So x is equal to 4 cosine 2 pi over 3. Y is equal to 4 sine of 2 pi over 3. All right, so 4 times cosine 2 pi over 3 in the second quadrant, cosine's negative in the second quadrant. 60-degree reference angle, cosine's equal to a half, negative 1/2 because it's in the second quadrant. All right, 4 sine, second quadrant again, sine is positive, this time radical 3 over 2. So negative 2 rad 3. And so therefore, you don't have to put the therefore, I just like doing it. All right, x, y, z, negative 2 rad 3. The z is equal to z. I almost wrote a z. Negative 2. All right. So then all we'd want to do is verify that that's equivalent to the polar coordinate. Well, I go back and forth. I just want to warn you about that. I go back and forth between saying polar and cylindrical. It's easier to say polar, so I tend to say that. You know, that's where my brain takes me. And also, I kind of look at it like cylindrical. Yeah, okay, it's a circle with height. Great. Yes, there are cylindrical coordinates. However, its basis is the polar coordinate system. It's a polar coordinate system with height. You know, so the only thing that makes it unique is that x and y's become r's and thetas and vice versa. So if I say polar in this context, I mean cylindrical. I'll never mean it the other way around. All right. So I just want to forewarn you about that. All right. But if you have any questions about that, you'll let me know. All right. So what we're going to do is plot, or at least do our best to, because it's going to be a perspective drawing, negative 2 radical 3. So 2 radical 3 is about 3.5 roughly, and then negative 2 on this graph. All right, so negative 2 in the x direction, then 3.5 in the y direction. So 1, 2, 3.5, and then from there, let me just make sure that's 1, 2, 3.5, and then down 2 from that location. All right, so that's a little bit trickier. Here's 2. We just want to see if that's going to get us to the same point roughly. You know, it's really just a verification, and it's a hand-drawn perspective diagram. I mean, it's not going to be perfect, but it looks pretty close. All right. So if you plot, again, 2 units in the negative x direction, about 3.5, you know, a little bit less than that in the y direction, positive y direction, and then down 2 in the z direction, then that'll get you to about right here, which is pretty close to where we ought to be. So I'm not doubting that my values are correct. All right. So the question becomes, well, which way is easier? Well, it depends on what you need it for. All right. Because you might look at it and say, well, we were doing just fine when we were plotting with x comma y comma z. Why do we have to switch over to this? Well, if you go back to some of the examples that we talked about in terms of the volume, you'll see that there's some integrals that are just nasty when it comes to the rectangular equivalent. But if you put it in polar, or when we get to its spherical coordinates, you see it becomes a whole lot easier, right? So that's kind of where we're at. It's, yeah, and you'll see in a few minutes. Right, so this won't be one of those teasers where it'll be like, oh, just wait till the end of the course, you'll see it all play out. No, it'll be in a few minutes. All right. Rectangular coordinates to cylindrical coordinates, just so I don't have to write it all again. Take my rules. Make it small and zoom it. All right, these are rectangular coordinates, which means they're given in the form of x, y, z. All right, so what I need are r, theta, z. Well, again, z is z, so I'm good there. So my highlight, I want that on these guys. All right, because I want an r and a theta. I don't want an x and a y. So r is going to be equal to the square root. Come on, give me a radical. Okay, good. 1 squared plus -3 squared. So 1 plus 9 is 10, so root 10. Then theta is going to be equal to the inverse tan of -3 over 1 inverse tangent of y over x. A little bit of a different story, not really a clean value. I mean, if it were a radical 3, we'd be in good shape, but it's just a -3. Right. So what we can do is take a quick look. Let me hit a new field here. Inverse tan, -3. See what we're up. Pretty ugly. I mean, I could put its approximate value down here. Default setting on Desmos is radians, so 249. All right, you can double check by hitting on that wrench just to make sure you see it's radians. If you wanted degrees, tap on degrees. You see it's not much better. I'm putting it back to radians. All right, so one way you could write it would be to say radical 10, comma, -1.249. That's r comma theta, comma 5. All right. So I put a little GeoGebra diagram in here just so we can kind of get an eyeball on it. But you're looking at it from the perspective of the x-axis. Right. So this is the x-axis here. It's hard to see, but that's the x-axis. I'll zoom in a second. But just to actually get a decent understanding, it's roughly about -72 degrees from the x-axis. So we can kind of hold that thought. If I'm going radical 10 in the direction of -72 degrees, it's basically saying I'm going the length or the radius of a circle that has a radius of about 3.1. So I can kind of eyeball that. You know, it's not going to be pretty, but you know, just kind of finagle it a little bit. So this would be a radius of 3 and change. I'll put it over here, I guess. So I'll write the radical 10, that's the radius. All right. So any point along that circumference is going to have that same radius. All right. So that jives. That's this length here. Also a radical 10. The angle. I don't know that that's exactly -72 degrees, but, or actually it shouldn't even be -72 degrees, -72 and change, but it could be. I mean, it's acute, less than 90, not a whole ton less than 90, but we could say that this is about the inverse tangent of -3. Let me just clean that up, move it over a little bit. All right. So what I did here is I plotted on GeoGebra, I plotted the original point, which went 1 unit in the x direction, 3 units in the y direction, and then whatever it was in the z direction, 5 in the z direction. So it went 1 unit in the x, 3 units in the negative y is what I meant to say, and then 5 units up. All right, that got us to point A. So this is 1, -3, 5, but it also happens to be radical 10 inverse tangent of -3, 5. All right, either way would be acceptable. Now you may wonder, and I think this is a pretty valid question, is it okay to leave it in inverse tangent form? My answer to that question is yes. If it doesn't give you a clean answer when you evaluate the inverse tangent. Right, so you see here, the inverse tangent of -3 gives you a disgusting decimal. If that happens, let's say on a test, you get a disgusting decimal when you evaluate the inverse tangent, you have my permission to leave it as the inverse tangent. All right, I believe from my experience, you'll have most people's permission to leave it that way because that's the more exact representation, right? There are some people who are kind of sticklers when it comes to that, where it's like if you can convert it over to a different trig form, like for example, maybe it's ugly as a tangent, but it's not so bad as a sine. If you can convert the inverse tangent to an inverse sine or some sort of ratio of trig functions, that they would ask you to do that. I'm not going to ask you to do that because I feel like that's more for a trig class than for calculus. So, but that's my personal philosophy. All right. So anyway, we got something that's equivalent, which is good, which means that we're on the right track with these rules. But what we want to do is we want to graduate to different types of functions. We don't want to just work with points. So here in numbers 3, 4, and 5, we're looking at some just basic equations, three-dimensional equations that have polar aspects to them. All right. So you see, for example, the r squared plus z squared is equal to 9. That's actually a nice easy one, because if you recognize that r squared is the same as x squared plus y squared, you already have the plus z squared is equal to 9. This is the equation of a sphere. With radius of 3 and center at the origin. All right, so that's actually not too bad. Quick substitution gets you a pretty good understanding of what's going on. However, if you solve this for z in terms of r squared, so just kind of play this out, you would have z squared, for quality z, is equal to 9 minus r squared. All right. Now you'd have plus or minus. If I can get a radical, I'll put the plus or minus, and maybe my penmanship just kind of knew that I should have put the plus or minus in first. I don't know. All right. So these two things are the same. All right. So these are the same. One is a multivariable function. The other is a function of a single variable. Z solved, yeah, it's got the plus or minus radical, but it's a function of a single variable. So if I'm looking to differentiate here, I don't need to differentiate in the partial sense or anti-differentiate. I don't have to use multiple integration. I could just use ordinary single variable integration or differentiation, right? So yes, I can recognize what it is better in rectangular form from experience, but I can work with it more efficiently in polar form, right? Cylindrical. Right, so that's number 3. Number 4, we have theta. Let's kind of pull that down here. Okay, try that again, shall we? Theta is equal to pi over 4. Now we know that theta is equal to the inverse tangent of y over x, among other things, but that's going to be the most useful way of representing it. Now, what I could do is take the tangent of both sides here and get y over x, poor quality y, is equal to the inverse tangent of pi over 4. All right. Oh, sorry, inverse tangent. Jeez Louise. That was something. Tangent of pi over 4 is equal to 1, so y over x is equal to 1, which in turn means that y is equal to x. Now, if we had no experience with three-dimensional calculus, and if I didn't tell you that we're working with cylindrical equations implying three-dimensional relationships, you'd look at this and say, oh, look, a line. All right, but this is a plane. All right. So this y equals x is happening for all z. This is the equation of a plane. So what we now have is a sense of what form, there's many forms that a plane can take in cylindrical coordinates, but we now have an idea of what it would look like in some cases, right? So if I wanted to, let's see, DHEPA equals, I honestly can't remember if this works. I'm going to find out in a second. Oh, not function. Polar coordinates. Nah, it's not going to let me. All right, but what I could do is type in y equals x. That's what pi over 4 looks like. Now, if you give that infinite height, because remember, we're looking down on the xy plane, you give that infinite height, look at it from a side view, then you're looking at a plane, basically a plane that's orthogonal with the xy plane, right? So it's a pretty cool relationship, but it's basically telling us that everything we knew about lines is still going to apply the same way. Lines, as they translate to three-dimensional relationships, they're going to translate into polar coordinates the same way. All right, z equals r. All right, that's going to be a fun one. All right, my work's getting a little messy here. Let me do a brief little modification. Make that purple. So z could be thought of as equal to the square root of x squared plus y squared. I could square both sides. All right. Now, I could also leave it as z equals the square root of x squared plus y squared. I mean, that's something to keep in mind. But if I wanted to get it into, some sort of, I'll call it standard form. I mean, I didn't coin that term, obviously, but if I wanted to try to make that look a little bit more recognizable, I could get it in this form instead of equal to 0. There's a bunch of things I could do. All right. But it's in rectangular coordinates now, so we could take a look at it in GeoGebra and see what's going on. We could also try to make it look more reasonable algebraically, but it's going to be a tall order. All right, so that's not what I want to do. No, not Food Network. Oh, okay. Well, in case you wanted to know how to make Instant Pot chicken adobo, it's very good. Delightful, traditional Filipino recipe, if you didn't know. Honestly, it's pretty easy recipe. All you need, recipe being the word of the day. It's pretty easy recipe because all it is really is soy sauce. They call for like a half a cup of soy sauce and anywhere from 3/4 of a cup to a cup of vinegar in the Instant Pot. Like I like it a little bit more with the soy sauce. So what you do is you chop up an onion. You put in whatever you want with it. Like some people put in like carrots or potatoes or whatever. But you brown some chicken thighs. Season it any way you like. All right. You brown the chicken thighs. You put it in the Instant Pot. But I put in a cup of ponzu sauce rather than soy sauce. All right. I like the citrusy flavor. It breaks down the tendons of the chicken thighs a little bit better, but it has a nice delicate flavor. But then a nice sharp contrast with the citrus flavor and the vinegar flavor. A bay leaf. You put some people like to put garlic in there. Some chopped garlic. Half an onion, half a medium-sized onion, sliced. Right, you create the rings. Just pop that in there, and then just put it on for whatever the poultry setting is on the Instant Pot. Usually about 15 minutes. But then the key to everything, you take the chicken out, put it aside, leave the juices, everything in the Instant Pot, and reduce that for 20 minutes. then pour that sauce over the chicken and have some white rice to go along with it. Can't go wrong. Delicious. And so, that's my modification of the Filipino chicken adobo recipe. Anyway, you know, I gotta say, when I accidentally open a private browser, you get like food recipes. I'm sure there are other people out there when that happens, they're looking for a new line of work, you know. So me, I got nothing on it. So I'd talk cooking all day. I should teach a class on that. Not always healthy though. Not always healthy. Right? So, and I can write all that down if anybody's interested, you know, because I know that you know, like I go off the cuff on stuff like this, and people are like, "Hey, it's funny and everything," and then later on they're like, "You know, that sounds pretty good. Let me give that a shot." You know, so if anybody's interested, I can. Will it be on the test? Maybe. Let me see. I'll see if I can make it a bonus question, like what do I use instead of soy sauce in the Instant Pot recipe for Filipino chicken adobo? And then you'll say ponzu sauce and you'll get the credit. I don't know. I'll figure out something. Make it worth your while. Listen to me go up ramble like this. But if anything, you'll have a delicious meal out of it. So Z equals x squared plus y squared. Look at that. That's insane. It's like one of those, you know, those paper cups that you get when they give you the fries at Citi Field, when you go to the I forget what the name of the French fry place is. It's in home run territory, but they give you it in that cone shaped napkin, you know. But actually, what it is supposed to be is a circular cone. Right. If you zoom out at first glance, you know, like you look at it too closely, it doesn't look quite right. But what it is actually a cone. And it's kind of cool. And so this is a cone. Right. Specifically, it's a right circular cone, but you know, like I'll show you other types of cones as we go forward, and you'll see that, you know, it doesn't really enter into the realm of necessity that we call it a right circular cone. It's more, you know, for a geometry class, right? But you can see it's a circular type of graph, right? So a plane by definition is defined rectangularly. So generally, the most efficient way of defining a plane would be in rectangular coordinates. For example, if I'm talking about a plane parallel to the XY plane, it's just simply Z equals a constant. That's pretty nice, right? But a cone, a sphere, those are all circular. So it would make sense to work in circular form, circular coordinates, to be able to evaluate these sorts of things, right? So what I did here, just so I wouldn't bore you too much, is I typed out the proof for coordinates. I can't even blanked out there for a second. Cylindrical coordinates and finding the differential areas leading to volumes. All right, but I'm just going to talk you through it, and I'll show you different proof in a few minutes, because the one I do is actually a little bit more user friendly, but it does rely on prior knowledge. All right, this one is kind of from scratch, so people kind of like it a little bit more in some cases. But if we're looking at, for example, some bounded region in the XY plane, right, and that bounded region is circular in nature. If we were to find an area in polar coordinates, you think back to what we did in the first unit, we used 1/2 r squared d theta, right? With the idea being that if we ever wanted to find the area between two polar graphs, we would just subtract the two, right? But the important thing to keep in mind here is that we're making a movement in terms of theta based off of the variable r, right? So this r, for example, could be vastly different from this R. Right? Because if it's variable, maybe one of them is like 10 and the other is like 8 1/4. I don't know, something different. But the idea, let me get this mouse out of the way. The idea is that there is a change, right? It's not a constant. If it were a constant, we would just find area the old-fashioned way, pi r squared. All right. But we do have that movement. What we learned way back when we talked about polar coordinates is that every point is part of its own circle. It's the radius of its own circle. And I drew the giant circle for this blue radius, and I drew the giant circle for the purple radius, showing that they were part of different circles. So I don't think I need to go down that road again. Right. But there is that movement of theta that gets you from one to the other. But what we do is, instead of, let me do this in a nice thin bright red, we don't just make one sweeping movement from one point to the other. We take little infinitesimal movements getting you from one to the other. So in that little infinitesimal distance, that little schmidge there, we call that d theta. All right. Instead of saying theta, one sweeping movement, we say it's an infinitesimal movement that we call d theta. And then we repeat that process over and over again, integrating it so that we get it all together to give us that bounded region. All right. So what we're going to do is that with height. And that's it. All right. So by simplifying that relationship, 1/2 r squared delta theta, I call it here, as opposed to d theta, because I am doing it over a not infinitesimal region, just for the purpose of being able to display it. We call that delta theta, but when we minimize it, we call it d theta. All right. So when we get it down to the infinitesimal level, it's like the slope of a secant line, change in y over change in x, versus the slope of a tangent line, dy dx. Right? We bring it down, we limit it, bring it down to the instantaneous level. The capital deltas become lowercase deltas, which then get abbreviated with d's. Right? So there's that proof for you, but I like a different one. And I'll show you that other one. Oh, geez. Okay. Where's my other proof? Did I delete it or something? I don't know. Okay, well, I'll show you the other proof in a few minutes, and then I'll talk to you about how you can get some typo bonus for that. All right. So Fubini's theorem involves the idea that we can apply a multiple integral over some interval related to theta, and then some other interval related to r, or vice versa. All right. But yeah, I don't know what happened. Where I must have deleted it. Anyway, my little proof. I don't know what happened. I have a proof that I wanted to show you, but it disappeared. So I'll just do it off on the side here somewhere. All right. And it's because this r dr d theta, if you like the proof on the previous page, then most people are satisfied with that. But I like the idea of saying, well, we worked with r dr d, or we're working with r dr d theta, but before we were working with dy dx or dx dy. Well, how do you get from one to the other? All right. So I guess I'll just do it off on the side and just regret it later that I don't know. I must have done it to save space or something, but I could have sworn I had it here. Anyway, let's say we have dy dx, a double integral dy dx, and I read a z. Right. We know x is equal to r cosine theta. We know y is equal to r sine theta. All right. Those are relationships that we talked about in the first unit, and we just kind of reviewed them a few minutes ago. All right. So that's nothing new. I can make this a dx d something, dx d whatever I want, within reason, of course. I mean, either dx dr or dx d theta. You know, pick the one you want. I'm going to go d theta. All right. So now this is an ordinary derivative from Calc 1 in the sense that both r and theta are variables. I'm not treating one of them as constant, right? So it's not a partial derivative, right? It is the derivative of a multivariable function where both variables are treated as variables. So this requires implicit differentiation, all right? If I could treat one of them as constant, then that would be a different story, but there's no reason for me to think that I can do that. All right, and I'll show you instances down the line where you can make a decision to treat one as constant, because we do have to cross that bridge. How do you know when you see a function like this as opposed to a function like that? It's all coming. All right, so dx d theta, first times the derivative of the second, so r times the derivative of cosine theta with respect to theta would be, negative sine theta. All right, so it's with respect to theta, so we're good there, plus the second function, which is cosine theta, times the derivative of the first, that derivative of the function r with respect to theta can only be written as the derivative of that function r with respect to theta. All right, so what I can do here, if I want to try to clean it up, and in fact, the only thing I can do is multiply both sides by a d theta. And honestly, if I'm reflecting back, if I'm being honest and reflecting back to the first unit, I'm pretty sure I remember confusing the living daylights out of myself when I showed you how to derive the formula for dy dx, you know, dy over dx, the derivative in polar coordinates, because I was in my mind trying to do this. All right, so just quick double check, negative r sine theta d theta plus cosine theta dr, because I'm essentially just distributing this d theta to each term here. So here and also here. All right, so now I'm just going to do the same thing. I'm going to do the same thing with the y, dy d theta. So first times the derivative of the second, so r cosine theta with respect to theta is just cosine theta, plus the second, so sine of theta, times the derivative of the first, dr d theta. Now I'm going to multiply both sides, like I did previously, by a d theta, or quality anything. Cancel, cancel. We're looking at dy is equal to r cosine theta d theta plus sine theta dr, or quality d. All right, so we're going to multiply these two things together, the dx and the dy. And the reason why we're going to do that is because when we find a multiple integral, if you just think back, the multiple integration, we would have a double integral, then we'd have some z function, and then we'd have dy dx, or we'd have dx dy. Didn't really matter, depending on if it were rectangular bounds, it wouldn't matter. But you know, instead of doing both, I'm just going to do it the one way and trust that you'll believe me that it works the same way for dx dy, you know, because multiplication is commutative. All right, so dx dy is going to be equal to, now it's going to be pretty hairy here, so I'm going to move it over there. So we're going to have the negative r sine theta d theta plus cosine theta dr multiplied by r cosine theta, or quality theta, d theta plus sine theta dr. and I'm going to distribute. And like I said, it ain't going to be pretty, but we can do it. So sine theta d theta multiplied by r cosine theta d theta is going to be negative r squared sine theta cosine theta d theta squared. The outers, that's going to be negative r sine squared theta d theta dr. Right? Then the inners are cosine squared theta d theta dr. So I'll just kind of chuck that down here. Plus sine theta cosine theta d theta dr. So that's what dx dy is equivalent to, at least at first glance. Now this will simplify, and there's always a chance that I made a mistake algebraically, so I'll double check that. But we want to be thinking about how we can clean this up somewhat. Where I find out where I screwed up. Most likely. Yes, thank you. Now I can move it over. All right, so we have some common factors. We have some things that could be put together. All right, so the middle terms, if you look at those, let me get this up. We could put the middle terms kind of sort of together. They have a common r dr d theta, or d theta dr. All right, so that's what I'm going to do here. R, I'll write it as dr d theta. That's going to leave us with a negative sine squared theta plus cosine squared theta. All right. Now the other two, they have a common sine theta, cosine theta. So we can put those together. It's not a simple matter of me just writing a bracket. So I'll just kind of do my best and not make this look hideous. But we have a common sine theta, cosine theta, but we also have a d theta that could be factored out. All right. So I'm just going to kind of chuck that off in the beginning. You know what? I'm going to move this over a little bit. Schmidge that over that way. So I'm going to pull out, like I said, the sine theta, the cosine theta, and a d theta. Yep. That's going to leave me with a negative r squared d theta, all right, plus dr squared. And that's all plus that other expression. All right, so still not very attractive, but getting there, believe it or not. All right, so it's really going to come down to those trig functions, the sine theta, the cosine theta, in both cases. All right, and so what we actually end up needing to happen is kind of a weird thing to say, is we need to actually minimize those. All right, so those actually have to go to 0 in order for this to play out in any reasonable way, right? So what's going to end up happening, the sine ratio, again, that's y over r. We know that y isn't going to be, I'm sorry, the r isn't going to be changing. It's dependent on whatever the function is. But we do know that y, if we're going to minimize, has to go to 0, right? So what we do is we replace yellow, my sines with y over r. And I replace my cosines with x over r. All right. And so what we're going to end up doing is limiting this, because you can't send sine to 0 and cosine to 0 at the same time, because there's no instance in which that occurs. But what we can do is send sine to 0 and cosine to pi over 2, right? Or I'm sorry, we'll send them both to 0, but we can't send them to 0 at the same angle, is what I meant to say. I tripped myself up there. So it won't be a matter of saying I need both sine and cosine to be 0 simultaneously, at least for this piece. For the other piece, it will be that. All right. So if sine of theta is equal to 0, then cosine of theta is equal to plus or minus 1, and vice versa. All right, so we would want to be thinking, how can we send the sine function to 0? All right, so because if I were to say, okay, I'm going to let sine approach 0, then I would be forcing cosine to go to plus or minus 1. But if I convert it over into rectangular, or just those pieces, convert them over into rectangular coordinates, then I can kind of get around that a little bit. All right, so what I can do is I can let y go to 0. That would make sine go to sine of 0, which is 0. Right? That would happen if sine is equal to 0. I'm sorry, if theta is equal to 0. All right. And so what that would tell me, again, because that's where we run into trouble. If I let theta equal 0, then I'm letting cosine equal to 1, and that messes things up. Oh, actually, I'm sorry. Wait a minute. I was looking at the wrong thing. No, that's fine. If theta is equal to 0, then sine of theta is equal to 0, and cosine of theta is equal to 1. Right? That's actually okay. It'll simplify it down, but it won't simplify it down necessarily in a way that's, obvious. But let me just show you. So well, I already did the limit as theta approaches 0, dy dx, dx dy is what I want to write. So that would make this whole thing 0 out. But the other part, r dr d theta, times negative sine squared theta, so that would be times 0, plus cosine of theta, cosine of 0 squared, which is equal to 1. So we get r dr d theta as a result. All right. So what we're doing is we're sending the sine function to 0 because we're setting theta equal to 0, or we're sending theta to 0. I don't even know how I got that last sentence out. I barely didn't even do it right. So yeah, that's the idea, is that if we're restricting theta by sending it to 0, we're minimizing it. You know, that's the idea. It's like going back to calculus or early calculus, Calc 1. What do? We let our delta x approach 0, right? So if there was an x in the function, you know, and that was a variable, you know, there's a function of x, then we left that alone. But if there was an h, we replaced it with a 0. So it's the same idea here. We're leaving any r's and d thetas and drs alone, but anything else we got to do something with. And so since we want to minimize it, we would send our theta to 0, and then I'm just realizing I never really needed these. As a consequence of that, sine goes to 0, but cosine doesn't, but that comes out in the wash anyway. All right. So the other way that you could have looked at this, you know, aside from what's on the previous page, is you could have looked at this as the double angle rule for cosine. That's the same as saying cosine of 2 theta. All right. And this one you could have looked at as 1/2 of the double angle for sine. Simplifies things a little bit, but it requires you to know those relationships. In which case, it becomes a little bit more apparent that, yeah, while we're trying to restrict our theta so that it goes to 0, it will impact these in such a way that this goes to 0. Right, this one will go to 0, but this one will go to 1. All right. So that, for some people, that might be a little bit easier. I don't know. All right. So let me just clean this up a little bit. Yeah, I don't know where the space for all of this stuff went, and it's bothering me. There's no good place to put it, so I'll just put it there. Well, actually, no, there's a really good place to put it. I know where to put it. Oh, I wanted to cut it, not copy it. Ay, ay, ay. There we go. All right, so it got its own page. All right, so I went the wrong way. So this, after all of that, can now be replaced with an r dr d theta. All right, so that's our that's one way of proving it. All right, I like, you know, aside from all the uhs and all that crap, I like this one better because it takes what we already knew from the previous unit and it just kind of expands upon it rather than going back 2 units and trying to remember stuff that was barely really addressed. Right. So anyway, so let's tackle, now I'm going to go the wrong way with the page shifting. Let's tackle a problem that involves us using polar coordinates, because I think it's really cool, number one, that we can now have a system that allows us to convert over from one form to the other. You know, just for the sake of doing the math, it's just fun, I think. But then there's also the aspect that you know, I'd like to think this is going to make things easier, you know, and if it does, that's going to be a good thing. All right. So let's take a look at this problem. It says use polar coordinates to evaluate this unholy mess. All right. So you kind of look at this and say, all right, well, if I were to do this by hand, I would first have to anti-differentiate with respect to y, then anti-differentiate with respect to x. So that should be super easy, barely an inconvenience, right? No, that's going to be pretty terrible. It might not be that bad. You know, you might be able to do it, but if you go into any kind of problem that you see from here on out with the mentality of there's got to be an easier way, then you're on to something. All right. And so this is one of those situations. Situation being the second word of the day. All right. So we want to convert this over to polar form and see what's going on. But before we do that, let's get a look at the picture. All right. So the bounds, for example, bounds are going to be hugely important. Let's focus on the bounds for a second. So these are y bounds because, as you know, when we integrate inside out. Right. So we would be integrating with respect to y first. Right. Now, I mentioned in the last unit that hopefully you'd get to a point. I don't know where my Calc went. You would get to a point where you would be thinking, all right, what are our bounds here? Are they x equals? Are they y equals? And you might find yourself just labeling it as y equals, x equals, just to kind of keep things straight. Right. So if that's the case, then you're right where you ought to be, basically. Right. So we have y equals the square root of 4 minus x squared, and we have y as the upper bound, and y equals the negative square root of 4 minus x squared as the lower bound for equality squared. All right. Now, to get a sense of this, I mean, I could put it in Desmos, I could put it in GeoGebra, but why don't I just square both sides and see what's going on? Y squared is equal to 4 minus x squared. Same deal for the other one. All right, so that's a nice outcome there. That's telling me that they're essentially part of the same equation. All right, so if I add x squared to both sides, I'm looking at x squared plus y squared is equal to 4. All right, so that's a circle with center at the origin. And radius equal to 2. All right, now because it's centered at the origin, when I come up with the radius here, I'm actually coming up with the polar equivalent for that graph. All right, so the polar form is r equals 2. Now, I'm not incorrect when I say it's centered at 0, 0 rather than 0, 0, 0, because the bounds are representing the base area, right, in the xy plane. So it ought to be two-dimensional. All right, so we have that, but then it's saying the x values are only going from 0 to 2. So, you know, why don't we draw a quick picture of a circle and see what's going on there? Oops. All right, so Scheukel. That's a terrible circle. All right, that's slightly better. Like 12% better. All right, so that's my circle. Now it's saying that my x values are going from 0 to 2. All right, so let me just identify x equals 0, right? Yeah. And x equals 2. Well, it's circle radius of 2, so that means that it's right at the circumference. All right. So what this is telling me, and again, that negative radical is really important because that's the bottom half of the circle. So that this guy right here is referring to this part of the circle. Oh, that was lovely. I'll just do it that way. All right, so that bottom half of the circle. All right. So what it's saying is that we're filling this from bottom to top. And then from once we've done that, then we're cordoning it off so that we're only going from x equals 0 to x equals 2. So we're only talking about this part of the circle, the one that's double shaded. All right. So just to kind of make this less hideous, I'm just going to shade in the relevant piece. All right. So just this piece. All right. So then, all right, we're on to something here. But what if I want to think about this in polar coordinates, in the sense of that it's not going in terms of x and y, followed, it's not going in terms of y followed by x, it's going in terms of r followed by theta. All right. So what we'd actually be doing, and I'll start making my double integral here, is we would actually, when we think of polar coordinates, we're thinking in terms of circles. All right. So we would start off with a circle of a radius 0, then a circle of radius a little bit more than 0, then a little bit more, then a little bit more, then a little bit more, until we've occupied all the area in between. Oh yeah, that's just shaping up beautifully. So I'm building out in terms of r. I'm building out from 0 to 2. So if I want to make this go into my polar form with r dr d theta, I want it to go from an r value of 0 to an r value of 2. All right. Why the r? Because that's the first bound of integration, or the first variable of integration. Now, if I did r d theta dr, I could go the other way, but that's typically not what we're going to do. And one of the main reasons why we do that, if you think back to the last unit, we worked with the function first, and then we restricted our function. So our base area, we bounded with a function, and then we restricted our function, our bounding function in one variable with a constant in another variable. All right. So that's what we're going to do here. We're going to bound in terms of r, but then we'll bound our r in terms of theta. So then we want to be thinking, okay, well, if I'm starting at 0, to get one full turn around a unit circle, I'd go to pi over 2, then pi, then 3 pi over 2, then 2 pi. Well, I'm actually starting this whole process prior to getting to 0. All right. So this is my start. This is actually over here. This is before the start. This is 90 degrees or pi over 2 before 0. All right. So we're dialing it back pi over 2. So negative pi over 2 would be my start. That's my low bound for theta. And then my upper bound would be pi over 2. So the benefit of getting into polar coordinates, you see, we drew all these diagrams. You won't always have to draw the diagrams, right? We just have to do it the first couple of times to get a feel for how this all works. But then you start appreciating the cylindrical coordinates, because you start realizing, wait, I get to work with numerical bounds again instead of variable bounds. That's wonderful, right? That's what we want, right? Because if you look at the bounds of integration for the rectangular form, radical 4 minus x squared, that's terrible, right? How about 0 to 2? How about negative pi over 2 to pi over 2? That's not bad. The trade-off is that now we have to integrate this z equation, or z expression. I mean, the whole thing's an equation, but you know what I mean. This guy, but using the variables r and theta. All right. So we can do that. I was going to turn on the marker and draw it, but you know what? I'll just kind of put it in as we go. Y squared. Well, we know y is equal to r sine theta. So y squared is r squared sine squared theta. X squared plus y squared is r squared, all to the 3/2. And the r dr d theta is the replacement for dy dx. All right. So, what's that? Pre-game. Nope, no pre-game. Okay. So I just got to clean this up somewhat. Now this is going to be the square root of r squared is r cubed times another r is r to the fourth times this r squared that's there is going to give me r to the sixth sine squared theta dr d theta. Now I didn't forget the r. This r over here, I didn't forget it. I consolidated with all the other r's. I had an r squared here. This becomes r to the third, that's r to the fifth, multiplied by another r gives you r to the sixth. All right, so we're putting it all together. This is now going from 0 to 2 in terms of r, then from negative pi over 2 to pi over 2 in terms of theta. Now, looking at this integral, this double integral, and comparing it to what we had before, whole lot more manageable, right? So I'm looking at something here. If I anti-differentiate with this with respect to r, that's no big deal. No big deal at all, right? So 1/7 r to the seventh sine squared theta over the interval of 0 to 2. All right. The what you call it, the zero part is gonna work itself out. I'm not concerned about that. The sine squared part, that's going to be a little ugly if you opt to do it all by hand. I don't recommend you do that. I recommend what I've been recommending all semester, and that is put it in Desmos, let it do the work for you. But we do have to handle this r to the seventh power, which is I think 128, because r to the fifth is 32 to the sixth is 64. Double it one more time is 128. So 128 over 7 sine squared theta. We're integrating that over the interval of negative pi over 2 to pi over 2 d theta. And then that can go right into Desmos, because if you want to integrate sine squared by hand, you have to use a trigonometric substitution of 1/2 minus 1/2 cosine 2 theta. So not pretty. So stay away from that. Don't even bother. Just do it this way. Make sure you're in the right mode. You should be, again, by default in radian mode. So $1.28 over 7 times sine squared. I'll use x, close it up, dx, rather than the d theta. And we get something, I mean, it's nice or as ugly as every other answer we tend to get these days. So 28.723 approximately as the measure of volume, right? So definitely a whole lot nicer to do something like this once you get it into the appropriate form, right? But there's a lot of moving parts in terms of getting it into the appropriate form, right? Which brings us to number 2, which is the last problem we'll do today. Compute the volume of the solid formed by the intersection of the surfaces, right? So the intersection, if you look at that, you can see there's a little bullet-shaped area in the middle. That's what we're looking to find the volume for. It should be captured in between those two surfaces, all right? In order to come up with that actual volume, we'll need to figure out the volume below the top surface and the volume below the bottom surface, right? So you might want to take a look at that in GeoGebra, just to get an idea. Now you say, well, we already have the picture here. Yeah, but do you know which one's the bottom and which one's the top? I mean, I do from experience. I mean, but also it is parabolic in nature in the sense that it tends to follow the rules that we know from parabolas. So that, for example, that 5 minus x squared minus y squared could be thought of as 5 minus x squared plus y squared. Right? So that gives you a negative leading coefficient for a parabola. That tends to be a downward facing parabola. So I would tend to think that this is the cap to the bounded region, where the other one is the bottom. But you want to be sure, and you have the tools by which you can be sure, so why not, right? So that's the bottom one. And then the other one, I'll just type in, like I said, as z equals 5 minus parentheses x squared plus y squared. And you can see that that's the top one, or at least the cap to the function, or the boundary region. All right, so that's good news. Keep that in mind. We also got to find the intersection, right? Because if we're going to work our way out from the center, from the pole, we need to know when to stop, right? So that's going to be based off of this circular ring right here. We need to figure out where that terminates. All right, so that's going to be some circular region, but I can get that by finding the intersection between the two functions. So z is equal to x squared plus y squared, but also z is equal to 5 minus x squared plus y squared. All right, now, unless you have some love for rectangular coordinates that has something other to do with, other than familiarity to do with it, the idea would be to convert over to polar coordinates now, or cylindrical coordinates, because we know x squared plus y squared is the same as r squared. So this would be the same as saying 5 minus r squared. And this would be the same as saying just a plain old r squared. Since they're both equal to z, they're both equal to each other. So I can now say that 5 minus r squared is equal to r squared. Furthering that to say 5 is equal to 2r squared. Add the r squared to both sides, divide by 2. R squared is equal to 5 halves. Take the root. R is equal to, well, I could say plus or minus, but I don't think I need the minus, because as we know from rectangular coordinate, I'm sorry, two-dimensional polar graphs, if I graph a circle with a positive versus a negative, it's going to trace out the same path. Right? So I'm not worried about that. I am worried about getting the whole path. So I'll just say radical 5 over 2. Now, if you want to rationalize, by all means, go for it. I'm not going to require something like that. I mean, that's not necessary. All right. Yeah, there's nothing wrong. I've said this before. There's nothing wrong with having a radical involvement fraction. Whoever said that was a problem is just being difficult. That's one of those, when teachers say it now, they're only saying it because that's how they learned it. But there really is absolutely nothing wrong. And if anybody disputes that, you send them to me. Usually only the tutors that push back on stuff like that. So I've had to explain that kind of thing to more than a couple. Anyway, so we have an idea of the outermost part of these graphs. Now, what I want to do again is figure out the area trapped beneath the downward facing graph and the area that's above the upward facing one. Right? But the area above the upward facing one is going to be a little trickier to do. So instead of doing that, what we could actually do is find the area below the downward facing one, as in the area between the downward facing one and the XY plane, and then just subtract off the area, I keep saying area, sorry, the volume between the upward facing one and the XY plane. Right? So the way that would look is you'd have a double integral for the downward facing one, which we established was the 5 minus r squared. And again, that r d theta is just, at this point, I mean, if you got confused by my proof earlier, you're forgiven for that because I confused myself, as you saw. But there is that genesis of the idea that dx dy dx turns into, when we get into polar coordinates, cylindrical coordinates, it turns into r d theta, right? So I'm finding the volume that's trapped beneath that surface. And when we say beneath it, just like in Calc 1, Calc 2, when we would say the area under the curve, the area under the curve wasn't really under like infinitely. It was area beneath the curve and the between the curve, sorry, and the x-axis. Now it's between the volume between the surface and the xy plane. That's what this double integral is going to give us. All right. If I subtract from that, the double integral separating the z function of just r squared, or dr d theta, that's going to give me everything underneath this surface here. So if you look at this, just this piece here, this little bowl looking thing, it's not going to give me this part that I'm shading. It's going to give me everything but that. All right. So it's going to give me all of this stuff, the outer fringes. And so our first computation is going to give me all of this. Oh, that's very easy to see, right? Let me go something pretty bright here. Neon green. My first computation is going to give me this one. All right. Between that surface and the xy plane, all of it, everything. All right. That's what this one's going to give me. This other one is going to give me the one, obviously, that I shaded in red, which is all this fringe stuff that I don't want. And what will be left is the volume that I'm interested in. So that'd be great if I had the bounds. I don't have the bounds. Oh no. Why no? Well, if you really think about it, we're looking at a couple of different things going on here. One, that inner surface, right? It's going to begin, inner surface is a bad term. Let's focus on the red, right? That red one, it has a lot of volume beyond that circular region, right? The circular region that we care about, right? So we have to figure out all that and subtract that off, right? But for the purple one is just, it's the whole shebang all the way from 0, a circle with a radius of 0, all the way down to wherever that downward facing circle is going to intersect with the xy plane, right? So we need a couple of things. We need, where does the downward facing surface, so I'll write it over here, where, and I'll do that in purple actually. I'm going to give my color coding pretty consistent here. Where does z equal 5 minus r squared intersect the xy plane? The answer to that would be when z is equal to 0. So we'd be looking at 0 equals 5 minus r squared, right? And so that would be r squared is equal to 5, making r equal to, again, it's a circular region. That's this piece here. I don't care about a negative circle. A positive circle is fine, right? So the square root of 5 is good enough, right? So that whole region is going to start off with a circle that has a radius of 0, and then it's going to work its way out to a radius of radical 5, right? So that's actually pretty not bad. 0 to radical 5. And then you just ask yourself, okay, well, that circle, is it truncated in any way, like in number 1? In number 1, it was given in rectangular form, the volume. It told us basically, without saying so much, that we were only working with half of a circle. Is there any reason to think that we're not working with half a circle? If I were to draw the xy plane here, this circle here, I've already got it going from 0 to pi over 2. If it goes around the rest of the way, around the back, it's going to hit, so it's going to hit, start at 0, it's going to go to pi over 2, it's going to hit pi, it's going to hit 3 pi over 2, and it's going to hit 2 pi. It's going to go all the way around, right? So I'm not worried about truncating or restricting the domain here. So this should go from 0 to 2 pi, all right? So if I just wanted the volume contained between that, the one I highlighted in green, the surface in green, and the XY plane, I would have it just by doing this this formula, or this double integral. It's the other one that gets a little kooky. All right, so let me get rid of this purple business over here, because I don't really, it's going to make it a mess. This one is all right. All right, so as far as the R is concerned, for the other function, that's not too bad either, because we got to be thinking about, okay, well, where does it start and where does it stop? All right, well, that whole bounded region is going to start where the graph starts. All right, so it's still a matter of going out from that 0, because we do have a point here. All right, so this location, but we have to get to, and let me show you by getting rid of some of this mess. We do have a little transition here. If we go out from 0 to just this location here, we could subtract off everything underneath the curve, underneath the upward facing surface, underneath this curve, right? But then we'd still have this little bit of fringe going on here, this little extra business. Let me get a different color there, this pinkish color here. We still have this little bit of fringe going on here. That's got to be accounted for also, but you can see, hopefully, maybe not, it's kind of debatable. That's not part of the graph, the upward facing surface. That's not bounded by the upward facing surface. That's contained underneath the downward facing surface, right? So that first computation is going to get us everything underneath the green, right? So going back to this, everything underneath the green, all of this starting from the center and getting all the way out to the radical 5. But if I want to get rid of everything from that, the part of, I'll call it a bowl, the lowest point of that bowl, the minimum of that bowl, outward from there, I got to subtract off the piece that I have marked in red, followed by the piece that's marked in pink. All right, so going, or just focusing on the red, I can go from, that would be 0, and right up to that intersection here, which happens at R equals the square root of 5 over 2. It's still going all the way around. So this bowl here, if I'm trying to get all this region accounted for, so I'll just drop it down here. It's the same idea. This bowl-shaped region, if I'm subtracting off that red, it's still going to work its way all the way around. That point is going to work its way all the way around and take out and carve out all of that volume that we don't want. Since it goes all the way around, again, starting at 0, working its way to 2 pi, we would make the bounds from 0 to 2 pi, right? But we still got that little pink area that we have to account for, right? So for that, this is what makes it tricky. We have to subtract off another double integral. And that double integral is related to that first function, so 5 minus r squared, r dr d theta. But this time, it's starting at the intersection, which is radical 5 over 2, and getting all the way out to r equals radical 5. still going all the way around. So 0 to 2 pi, but there is that extra piece there that didn't seem like it was obvious or apparent initially. But that's the key to everything, you know? So you got everything underneath the green, and then you start carving away, you start chipping away. But it all has to do with visualizing things. Next class will actually show you how you can truncate some of these graphs. Just because I'm looking at the clock right now, and I don't want to burden you too much, but it has to do with a conditional, right? In GeoGebra. And there's value to it, because if you only want to focus on a certain piece of it, then it becomes kind of necessary that you start trimming it a little bit, right? Just debating on whether or not I should show you now. And it's kind of it's better served if I show you in rectangular form first before we get into polar. So I'll sit tight on that. I'm not gonna try to squeeze it in 2 minutes. All right. So what I'll do is, instead of that, I'll put a star on the next 2 problems. And so I'll make a video for one of them. We'll definitely go over one of them together in class next time, just because I think there is benefit to having a second look at this kind of problem together as a group, just so you could ask questions if you need to. And also, apologies, but you'll enjoy this one. It says compute the volume. For a lot of these questions, the priority isn't so much compute the volume as it is writing the integrals or sum of integrals that can be used to find the volume, right? So if you need some typo bonus, something that you could write would be page 74, number 2, change the directions. And that would actually be the same for numbers 3 and 4 on page 75, right? All we want are the actual integrals, because everything else is just calculator work, right? So I'm gonna leave it there. If you have any questions, stick around. If you came in late, check with me before you go. Otherwise, have a wonderful, wonderful weekend if you celebrate Easter, or I apologize, is it Passover, or any other holiday, you know, Mazel tov. If you enjoy, if you celebrate any of those things, I hope you enjoy, and I'll see you all on Tuesday.
Thank you, Professor.
You're welcome. Take it.
Thank you, Professor.
You're welcome. Take it.
Thank you, Professor.
Have a good one.